What do TVs, microwave ovens, satellite dishes, X-ray devices, and this baby's eyes have in common? They all use electromagnetic waves. In this unit, we will explore the 7 types of electromagnetic waves, from radio waves to gamma rays. And we will concentrate on the one that is perhaps the most common, visible light.
Light energy is one of the most important forms of energy in the universe. Light, through the process of photosynthesis, is the force behind all life on Earth. What is the nature of light energy? How is it produced? And what physical laws determine the behavior of light?
During this lesson, you will describe how electromagnetic waves are produced and transmitted through space. You will also list the 7 types of electromagnetic waves in order and give examples of and facts about each.
So far this semester, we've studied electricity, magnetism, and waves. Now, everything comes together for our study of electromagnetic waves. If you remember, there are 2 basic types of waves. Tell your teacher the big difference between mechanical waves, like sound, and electromagnetic waves.
Light waves are just one type of electromagnetic wave. Unlike sound waves that can only travel through matter, electromagnetic waves can travel through the vacuum of space.
Did you get it? Electromagnetic waves can travel through empty space. But there are other differences, such as how electromagnetic waves are produced. Now, when we studied electricity and magnetism, you learned that there is an important link between the two. You already know that Michael Faraday discovered that a changing magnetic field can produce an electric field. Well, in 1860, a Scottish scientist named Clerk Maxwell completed the picture. He proposed the idea that a changing electric field could then produce a magnetic field. And here's the big news. It turns out that you don't even need a wire or a magnet. All you need is an electrical charge that is vibrating in some way. Here's a very simple example. When I place a negative charge on this rod and move it, what kind of field develops around it? Tell your teacher. A moving charge produces a magnetic field. But when the charged rod slows down and stops, the magnetic field collapses to 0, doesn't it? So the magnetic field is changing as it grows and then collapses. And according to Maxwell, this produces what? It produces an electric field. Now what happens as the charged rod vibrates back and forth, starting, stopping, and changing direction? Remember your right-hand rules? A changing magnetic field produces an electric field. And a changing electric field produces a magnetic field. And so on and so on. Put your pencils down and watch this.
Let's look at a graph of what's going on as our charged particle vibrates back and forth. We'll pretend that our charged particle is like the bob of a pendulum. At the starting point, the charged particle is not moving, so there's no magnetic field, and so this point would be 0. As the charged particle accelerates inward, the magnetic field grows, and so does an electric field grow perpendicular to the magnetic field. At this point, our charged particle starts to slow down, and so the magnetic field begins to collapse, and so does the electric field. And so both fields are 0 at this point in the vibration. Then our charged particle changes direction, and the same thing happens at right angles to the way it happened before. As our charge vibrates back and forth, an electromagnetic wave propagates or moves on its own through space.
Now, before you pick those pencils up, let me tell you a little more about these waves. Maxwell did some complex math, and calculated the speed that these electromagnetic waves would have to move through empty space so that the fields would not gain or lose energy. In other words, they would obey the law of conservation of energy. And it turned out that the only speed at which electromagnetic waves could move was 3.0 times 10 to the 8th meters per second. Does anyone recognize this number? Tell your teacher. It's the speed of light, which had already been measured by other scientists. Well, Clerk Maxwell quickly realized that he had found the answer to one of the big mysteries of science. That night, Maxwell and his date were walking in a garden and looking at the stars. Maxwell asked her how she would feel about looking at the stars with the only man in the world who knew what starlight really was. He knew then, and you know now, that starlight and all light is energy carried by electromagnetic waves. By the way, the young lady must have been impressed. She married him. Now, pick up those pencils. It's time for some notes.
Electromagnetic waves consist of changing magnetic and electric fields moving through space at the speed of light, which is 3.0 times 10 to the 8th meters per second. Electromagnetic waves are produced by vibrating charged particles. Electromagnetic waves do not require a medium, but can move through a vacuum.
There are 7 kinds of electromagnetic waves, all produced by vibrating electric charges. And they all move through space at the speed of light, represented by the symbol c. So, how are they different? Tell your teacher. Did you get it? The frequencies and wavelengths of the waves are different. As the frequency of the vibrating charges increases, the wavelength decreases. Now, all electromagnetic waves carry or radiate energy, and the energy of the waves depends on their frequency. That's important. Better write it down.
The electromagnetic spectrum is a range of wave frequencies depending on the vibration frequency of the electric charges. As frequency increases, wavelength decreases. As the frequency of the electromagnetic wave increases, the energy radiated also increases.
Let's start by filling in this diagram with the 7 types of electromagnetic waves. Now you should know that each type represents a range of frequencies. There is no sharp division between one type and the next, and there will be some overlapping. The lowest frequency waves with the longest wavelengths are classified as radio waves, which include both radio and TV signals. Next comes microwaves. The next 3 types are closely related and easy to put in the correct order. First is infrared, then comes visible light, and then ultraviolet. Here's how you keep them straight. Infra means below, like the infrastructure of a city is all the sewers, pipes, and cables underground. So infrared means that its frequency is below the red in visible light. Now, ultra means above, so ultraviolet has a frequency above the violet visible light. Next comes X-rays, and the highest frequency electromagnetic waves with the most energy are gamma rays. You should know these in order from lowest frequency and lowest energy to highest frequency and energy. This should be pretty easy since you're already familiar with a lot of these. And you should know some facts about each type. We'll spend the rest of this program describing one type at a time. You'll fill in the blanks in your notes as we go.
The entire electromagnetic spectrum contains a broad range of waves of different wavelengths and frequencies. Visible light is only a small part of the electromagnetic spectrum. Our eyes are special receivers, sensitive to the visible light portion of the electromagnetic spectrum, while this radio telescope dish in New Mexico, pointed deep into the universe, is sensitive to the radio wave portion of the electromagnetic spectrum.
So, what kind of electromagnetic waves am I producing? Certainly not visible light. Actually, I'm producing a very, very low frequency of radio waves. But we need a lot more charge and a lot higher frequency to do any good here. One way is to use alternating current, which makes electrons in an antenna move in one direction and then the other. The AC frequency can be changed to produce a wide range of wave frequencies. And of course, there are other, more complicated ways of vibrating charges to produce radio and other electromagnetic waves of even higher frequencies.
Now let's fill in some blanks in your notes. Of all the electromagnetic waves, radio waves have the lowest frequency and the longest wavelength. Television waves fit into this range. Before cable came in, TV stations were often described as having either VHF or UHF, which means very high frequency and ultra high frequency. Radar waves are the highest frequency radio waves. Each radio station is assigned a certain broadcast frequency.
This is the Peach Star radio station, WSTR, broadcasting at 800 megahertz and bringing you this question. In this statement, physics, fact, or fiction, radio waves cannot be heard.
Yes, it's a fact. No one can hear radio waves. So how can sound be transmitted to our radios and TVs? Well, a microphone is like a generator. When I speak into it, the vibrations of my voice are converted into electrical impulses. Watch what happens next.
The radio wave has a certain frequency which is different for each radio station in a region. This wave will act as a carrier wave. Now, this is the sound wave that has been converted to an electrical impulse by a generator. This wave is always changing because the sound is changing pitch and amplitude, and its wavelength in reality is much, much longer than the carrier radio waves. Now, when the sound wave is combined with the carrier radio wave is changed or modulated in some way. In this case, the amplitude is modulated. This happens on AM radio stations. AM stands for amplitude modulation. In this case, the frequency is modulated, and that's FM, frequency modulation.
Whoa. So, the radio waves carrying the sound signals are amplified and transmitted through the air. Right now, lots of different radio waves sent out by lots of stations are all around me. In fact, they go right through me, but are stopped by the metal in this antenna. So, how does this radio receiver know which frequency to pick up when I change the station? See if this sounds familiar. When you tune your radio to a station, you set one particular frequency at which the electrons in the antenna are allowed to vibrate. And the radio waves that match this frequency will make those electrons vibrate sympathetically. What is this phenomenon called? Tell your teacher. Yep, it's another example of resonance. And the radio receiver acts like a motor, converting the electric audio signals into motion in the speaker, making sound.
Microwaves are like radio waves, but have a shorter wavelength and higher frequency, making them slightly more energetic. Microwaves are used in satellite communications and in radar imaging. Microwave ovens are used to heat non-metallic materials.
You may have heard that microwave ovens cook food from the inside out. And conventional ovens cook food from the outside in. What does that mean? Let's start by talking about how conventional ovens work. The heating element in an electric oven, or the gas flame in a gas oven, gets really hot. Air molecules next to the heating element touch it and are forced to vibrate faster. These hot molecules jostle their neighboring molecules, and so on and so on. Then, the hot air next to the bread dough jostles the molecules on the surface of the dough, which are forced to vibrate faster and get hotter. And they transfer the heat energy to the next layer, and so on throughout the dough. This is called heat conduction, since touching molecules transfer the heat. Meanwhile, the hot, dry air in the oven evaporates moisture from the outside of the biscuit, causing it to get crisp as it continues to cook. If you set the temperature of the oven too high, the outside of the bread will burn before the inside gets a chance to cook. Now watch as our students do some cooking with a microwave oven while you hear about how it works. And fill in the blanks in your note-taking guide.
In a microwave oven, the electromagnetic waves penetrate the food fairly uniformly throughout. And very large molecules such as fats, proteins, and carbohydrates begin to vibrate sympathetically because the electromagnetic waves have matched their natural frequencies. The vibrating molecules produce heat, which cooks the food from the inside. Meanwhile, air molecules are too small to be excited by microwaves, so the air inside the microwave oven stays close to room temperature. That's why foods cooked in a microwave often don't get a crisp brown crust. Microwaves are not absorbed by most glass, plastic, and ceramic objects. The containers get hot only after the food cooks and transfers heat to the containers by conduction. Metals reflect microwaves and can cause fires or damage to the oven itself. They should never be used in a microwave oven.
See all the steam coming out of this bag of popcorn? Well, water is one of the main molecules that absorb microwaves and vibrate sympathetically. But water molecules are small and shouldn't have a natural frequency in the microwave range. Well, if you remember your chemistry, water molecules are strongly attracted to other water molecules because of hydrogen bonding. So they act like much larger molecules and form steam in a microwave oven. That's why you should prick holes in potatoes before microwaving them, to let steam out and avoid a food explosion.
Here's a challenge for you. Why do microwave recipes include a stand time after the food is removed from the oven? Think about resonance and tell your teacher.
When you stop pushing a child on a swing, does the child stop swinging immediately? No. And it's the same with vibrating molecules. Even after you take the food out of the oven, it continues to cook itself. That's why recipes include the stand time. If an egg were completely done when it was taken out of the microwave oven, it would be as hard as a hockey puck before you got it to the table. Okay. Enough about microwaves. Let's move on to the next type of electromagnetic wave.
Infrared rays are located next to the lower frequency red end of the visible light spectrum. Infrared rays are easily absorbed by matter and converted to heat energy. When you lay on the beach on a summer day, the warmth you feel is from the infrared rays of the sun.
The main source of infrared waves is the motion of regular-sized atoms and molecules. So all objects emit infrared radiation in the form of heat. That's why these waves are sometimes called heat waves. Of course, the heat we feel from the sun, a fire, or a radiator are all examples of infrared waves. Infrared radiation can also be produced electronically. One example is the heat lamp that keeps your fries warm in a fast food restaurant. Some animals can detect infrared rays. Rattlesnakes have sensors that allow them to find warm-blooded animals even in the dark. Geologists use infrared-sensitive film in special cameras to detect underground lava flows or find oil deposits. Your teacher might want you to find some other uses for infrared photography, such as in medicine or the military. Now, while our skin is sensitive to infrared waves, our eyes are sensitive to the next type of electromagnetic wave, visible light. We'll be devoting the rest of the school year to the study of light, but for now, just get the basic facts of light.
Visible light is defined as electromagnetic radiation to which human eyes are sensitive. Surprisingly, the range of visible light frequencies makes up less than 1/millionth or 10 to the negative 6% of the electromagnetic spectrum, so this space in here should be much, much smaller. The different frequencies of visible light are seen as different colors. From red with the lowest frequency and the least energy, to violet with the highest frequency and the most energy. We'll talk about how visible light is produced in the next program. But now it's time to go on to the next type of electromagnetic radiation.
Just past the high-frequency violet end of the visible light spectrum are ultraviolet rays. Ultraviolet rays, like infrared rays, are produced by the sun. The high energy of ultraviolet waves allows them to penetrate and damage living cells. Overexposure to ultraviolet radiation can cause sunburns and ultimately skin cancer in humans. The destructive power of ultraviolet radiation is also used in medicine to sterilize surgical instruments by killing bacteria.
As you just saw, after visible light, electromagnetic waves start getting dangerous. Now remember that all 7 types of electromagnetic waves are ranges of frequencies. So the lower end of the ultraviolet range, sometimes called UVA waves, are just a little higher in energy than visible violet light. UVB waves are even higher in energy and cause sunburns and skin cancer. But they can also be used to kill bacteria and sterilize medical instruments. Most of the highest frequency ultraviolet waves are blocked from reaching the Earth by gases in the atmosphere like ozone. That's a very good reason for protecting the ozone layer, which is destroyed by the chlorofluorocarbon compounds found in some aerosol sprays. You are probably pretty familiar with ultraviolet waves, so let's see how you do on this challenge.
Is this statement fact or fiction? Sunlight through a window can give you a sunburn. Tell your teacher. It's fiction. Ultraviolet waves cannot penetrate glass. When you feel your skin getting hot from sunlight coming through the window, that's infrared waves, which don't cause sunburns. Are you ready for the next type of electromagnetic wave? Watch this.
X-rays and gamma rays are electromagnetic radiation with even shorter wavelengths and higher energy than ultraviolet radiation. X-rays, which were discovered in 1895 by the German scientist William Röntgen, are capable of penetrating all types of body tissue. More dense tissue, like bone and tumors, absorb more X-rays than do less dense organ tissues. This property makes X-rays useful in medicine for producing images of the skeleton and other body structures. However, X-rays can cause changes called mutations in the cells they pass through. These mutations can lead to the development of cancer and other diseases, so exposure to X-ray radiation must be carefully controlled.
Do you know how X-rays got their name? A German scientist named Wilhelm Röntgen discovered them by accident in 1895. He called them X since they were an unknown type of radiation, and the name stuck. Because of their high penetrating power, they are used to take pictures of your bones or the contents of your luggage. Now we're ready for the highest frequency electromagnetic radiation, with the most energy of them all.
Gamma rays are given off by decaying radioactive substances and have greater penetrating power than X-rays. People who work in nuclear power plants where radioactive fuels are used are closely monitored for exposure to gamma rays. Astronauts wear heavy suits in space to help protect them from the high levels of ultraviolet, X-ray, and gamma radiation found in space, since the Earth's atmosphere is not present to absorb these high-energy rays.
So far, all the electromagnetic waves we've studied could be produced electronically, with X-rays requiring the greatest acceleration of the electrons. However, gamma rays are not produced by vibrating or accelerating electrons. These waves are generated during nuclear reactions, such as the decay of radioactive atoms or nuclear explosions. Gamma rays have the highest penetrating power of any type of electromagnetic radiation, and gamma rays can kill living cells. However, cancer cells are killed before healthy cells. Medical science has used this fact to our advantage in radiation therapy as a cancer treatment. Well, we've given you lots of information about electromagnetic waves today. Let's see how much you remember. It's time to show what you know. Jot down your choice for each question. Your local teacher will go over the correct answers with you.
Question number 1 is, all electromagnetic waves are produced by vibrating A, electrons, B, protons, C, neutrons, D, charged particles. Question number 2 is, the highest energy electromagnetic radiation is A, radio waves, B, gamma rays, C, X-rays, D, ultraviolet light. Question number 3 is, all electromagnetic waves move through space at A, 3.0 times 10 to the 8th meters per second, B, the speed of light, C, both A and B, D, neither A nor B. Question number 4 is, the concept of resonance explains A, the cooking of food by microwaves, B, the reception of radio waves by an antenna, C, the collapse of the Tacoma Narrows Bridge, D, all of these. Question number 5 is, TV and radar are included in which type of electromagnetic radiation? A, radio waves, B, microwaves, C, infrared waves, D, X-rays.
Remember how impressed Clerk Maxwell's date was that he had discovered that light is an electromagnetic wave? She married him, remember? Well, in our next program, you'll learn about some discoveries that made scientists wonder whether he was right or not. See you next time.